Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashudu Mamburo. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Welcome to term 3. Today we'll be focusing on knowledge area, electricity and magnetism. Topic being electrodynamics. Here we're talking about motors and generators. A very nice topic. You have done this topic, you've started in grade 11. So we'll as well look at your prior knowledge to say what do you know already and build from known to unknown. Now, these are the expectation or the objectives. By the end of this lesson, you must be able to understand these electrical machines, which is our generators and motors. Remember, learners, I want to make you aware that if we look at this term, it's all about the electrons that are flowing, the charges that are flowing, and it's all about that. You will see that you have a topic, this one, which is your motors and generators. You are having your photoelectric effect, you are having your galvanic cell and electrolytic cell. You will see the electron plays the important part in all these topics. So the first topic we're dealing with here will be these generators and motors. So we are saying the first thing that you must know at the end of this lesson is to state the energy convention. Very much important. So remember, we're talking about generators and motors. So you must be able to know that a generator, the name itself, generator, it generates. So a generator will convert mechanical energy to electrical energy. That is the first thing you must know. Energy convention. So a generator is generating electricity, so it must convert mechanical energy to electrical energy. I want to make you aware, don't make a mistake of confusing mechanical energy with chemical energy. Remember, chemical energy is in chemistry, mechanical energy is in physics. So here we're talking about mechanical energy. So that is the first thing you must be able to understand under this topic, to say a generator converts mechanical energy to electrical energy. That is the first thing you must know. So if you say define a generator, you will say it converts mechanical energy to electrical energy. And then when it comes to a motor, it converts electrical energy to mechanical energy, which means when you deal with motors, you are having an input of the energy. There must be energy source. So how do I know that this is a motor? It will have an energy source. How do I know that this is a generator? It must be producing the electricity. Hence, we are saying a generator, it converts mechanical energy to electrical energy. And a motor converts electrical energy to mechanical energy. So that is the first thing that you must know about these generators and motors, even in accordance to your exam guideline. Very much important that you know the energy convention. And then the second thing that you must know, it is the principle of electromagnetic induction. Here we're going to explain how generators work. So we're going to look at how generators work using the principle of electromagnetic induction. Already you can see we're having electro. I think you are thinking about electricity. You are thinking about charges, your electrons. You are magnetic, you are thinking about the magnetic field, which means there must be current, there must be magnetic field that we're going to talk about here. So that is your electromagnetic induction. We're going to look at that. That is the second point that you must know. The third point, you must be able to know the components. Very much important. If you want to know how generators work or how motors work, definitely you will look at the components. We have what is called AC and DC generator. AC stands for alternating. So you can hear from the name alternating, which means now there is periodically changes in terms of the current that is generated. And a direct current, DC means direct current, which means our current is flowing in one direction. So we're going to look at both AC and DC generator, and then we look at their components. How do you know that this is an AC generator? How do you know that this is a DC generator? And we're going to give state examples of the uses. Where do we use these AC and DC generators? So it's important that we look at the uses, and we're going to state energy conversion as already I've done this. We've stated energy conversion for motors. Remember, we said motors is M, start with M, so it's from electrical energy to mechanical energy. Whereas a generator, because it generates electricity, it means it's from mechanical energy to electrical energy. So you will have that in mind. And we're going to use the motor effect. You see now, with the motor, we use the principle is called motor effect to explain how a motor works. Remember, remember when we were dealing with the generator, we said a generator, it will use electromagnetic induction. But when it comes to a motor, it will use what we refer to as motor effect. So we can ask you a question in the exam to say, what is the principle that we use in generators? So for generators, we use electromagnetic induction. For motors, we use motor effect. Good. So all that these pieces of information I'm giving you, they're important for your understanding of this particular topic. And we're going to explain the functions of the components. Remember, we talked about the function of the components for AC and DC generator. Even when it comes to a motor, we have both AC and DC motor. So we have AC and DC generator, we have AC and DC motor. So that is important for you to understand. To say AC, we said is alternating current. So we have motors that are called alternating current motors, and we have motors that are referred to as direct current motors. So we're going to look at that, their components and their uses as well. And then we'll give the examples of the use of these motors, as we said. So this is our objectives for today that we want to do. But it's not only that. We're going as well to look at the advantages. What are the advantages of using alternating current over direct current? So we're saying there are some advantages of using AC instead of DC current. So we're going to look at that to say what is important here between the alternating current and the direct current. What is the advantages of using AC? You will understand that here in South Africa, we use AC current. The AC is the electricity that is being transported and transmitted. I wanted to say transmitted to your home. We are using alternating current. So we're going to look at the advantages of using this alternating current. Now, we'll as well look at the sketch of the graphs. Graphs of what? Voltage versus time. So it's not only voltage versus time. We'll have to look at the graphs of current versus time. So important objectives, because if you understand all these objectives, it means that you are ready for this topic. So know the graphs. Know that how do I sketch a graph of voltage versus time? How do I sketch the graph of current versus time for an AC circuit? And as well, we are going to define the term RMS for an alternating voltage. RMS for an alternating, we refer to it as VRMS. RMS for an alternating voltage. So that is VRMS. So when you say define VRMS, and then you are going to say the VRMS is the RMS value of AC. So we're starting with the AC. So we're saying the VRMS is the RMS value of AC. We define it as the DC potential difference, which dissipates the same amount of energy as AC. So we're saying VRMS, we're saying that it is the DC potential difference which produces or which dissipates the same amount of energy as AC. So we're just saying that this is the DC potential difference, and then that is it dissipates the same amount of energy as an AC. Now, even the same with the current, we'll call it IRMS, which is RMS for our current here. In that case, IRMS value, we are saying now it is the RMS value of AC, which is the current. The current IRMS is the current which dissipates the current of DC current that dissipates the same amount of energy as AC. So you can see that this one was saying is the DC DC potential difference that dissipates the same amount as our AC potential difference. So the amount of energy that is dissipated, it is the same. That is the more common thing that you must remember when you are defining your VRMS and your IRMS, because this question is asked as well in the exam to say define your RMS or for alternating voltage, or your RMS for our current. So you are able to say as to define them as we indicated. And remember, for all these definitions, we are using the exam guideline. So it's very much important that exam guideline, as we speak right now, you have the exam guideline next to you. You are ticking, you are underlining the keywords there. It is your working document. It is, some they refer to it as their Bible, to say always they are referring, as far as physical science is concerned, they are always going back to the exam guideline to say what are the expectations. Now, the other expectation is that we must be able to solve problems using these equations. So you'll find this in your data sheet. And as what we are saying to you now, we're saying when you start the topic, you are going to cut that exam guideline for electrodynamics and you paste it in your book. And you cut this data sheet and you paste it as well in your book. Why are you doing that? Because always you want to always refer back and look at the expectation of what you have to achieve by the end of the lesson. I hope that helps you, and now you have the picture or the expectation of what needs to be done. So that's what needs to be done under this topic. If you are able to cover everything we talked about here, you are ready for this electrodynamics topic. Now, we want to say you have started electrodynamics in grade 11. You have done this topic. I want to remind you that you have done electromagnetic induction and you have done what we call Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. And it is important that you revise these concepts. And so we are saying, as a grade 12 learner, you still have your grade 11 book, because all those things, we're building a house. Remember, NSC, we are saying it's a 3-year course. It starts in grade 10, it goes to grade 11. Now you are doing final year of the National Senior Certificate. The expectation is that you are having your notes from the previous grade, more especially grade 11. When it comes to this topic, you have done this Faraday's law, so you're able as well to go back and check and remind yourself what you have done under this particular topic. I'm telling you, if you do that, you will enjoy, you will see that everything that you are doing is adding up or is progressing from one grade to another. Now, you state the Faraday's law as the magnitude of the EMF, the induced EMF. I prefer to put it that way, to say the induced EMF in a coil is directly proportional to the rate of change of magnetic flux. You will see that we have that formula there. So you know that when you remove that number of tens there, you are able to say the induced EMF is directly proportional to the rate. The rate means, remember you've done rate of fractions. Rate means per unit time. So immediately we're saying the induced EMF is directly proportional to the rate of change in magnetic flux. So you are able to see that, this that is the change of magnetic flux. This one is the change in magnetic flux. So Faraday's law is saying the induced EMF is directly proportional to the rate of change in magnetic flux. Others would prefer to say is directly proportional to the change in magnetic flux and inversely proportional to the time. So you are still saying the same Faraday's law. You can use the one that you prefer, but both of them, as long as they are talking to what I've written there, you know that you know Faraday's law. So it's important. This is what you have done in grade 11. This is your prior knowledge, and you are acknowledging it. And we are saying in grade 11 as well, you were able to do activities as these ones. And this is what you need for you. Hence, I'm saying the importance of grade 11 is what is going to help you in terms of your understanding of this topic, and you'll be able to enjoy what you are doing. Now, let's look at this activity taken from a previous grade 11 question paper. It says, in which one of the sketches below is the induced polarity? Remember, we're talking about electromagnetic induction. So you can see that we're having a magnet and then we're having our coil there. So we're having our coil, we're having our magnet. Look what happens now. On the first number A there, where you can see that the magnet is pushed into the coil. So we're saying what happens when you push the magnet into the coil? According to the answer we've given there, is that the coil will induce a negative and will induce north pole. Remember, it is the north pole that is approaching the coil. When the north pole approaches the coil now induce the north pole. So you can see that the north pole, like terms, you were doing that, we're saying like charges, they repel. Even these poles, north and north, they will definitely repel. It means as the north is coming to, as we are pushing the magnet inside the coil, what happens? The magnet induces the north pole. Then it repels the north pole that is coming. So you can see as it comes, it does that. Now, let's go to number B. Number B is saying as the magnet is pushed, the north pole is being pushed towards the coil. What happens is saying the coil becomes the south, induces the south pole. No, that's not what happens. Remember, we are saying as the north pole approaches the coil must become north as well, induces the north pole there so that it can repel. So he's saying, no, I don't want you north pole close to me. I'm repelling you. I want you far away from me. That's how magnetic flux is being generated. And if you look at C there, if you look at C there, the north pole is going away. When the north pole, which means here the dark part is your south. So as the magnet is pulled out, what the magnet does, it says, now I want you to come back. You see what happens? As the north pole was going towards the coil induces the north so that it can repel it to say, I don't want you. But when the south now here is going away, the coil won't be south here. It must be north, which means this is incorrect. This is incorrect because we are saying as the south pole goes away, the coil will become the north pole so that it can attract it to say, come back, come back. That's when now we're having our magnetic flux. So you can see what is happening and how this magnetic flux is changing. What is causing the change in magnetic flux is the movement of the magnet into and out of the coil. I don't want you to think that it is at all times it is the magnet that is moving. Sometimes the magnet can be stationary. We move the coil in relation to the magnet. But there must be motion of either the magnet or the coil. One must be moving. So maybe you're asking a question to say, what happens when if I move the magnet inside the coil? We said that now there will be electromagnetic induction. But now, if I stop moving the magnet, what happens is that we will see that there is no EMF that is induced. So EMF is induced when there is a change. Remember, by definition, Faraday's law, we said the induced EMF is directly proportional to the change in magnetic flux, to the rate of change in magnetic flux. So we are saying now there must be change in magnetic flux. And what makes the change in magnetic flux is the movement of the magnet in and out of the coil. So if there is no movement of either the coil or the magnet, we are saying there will be no change in magnetic flux. And when there is no change in magnetic flux, we are saying the induced EMF will be zero. So immediately when I stop moving the magnet, the induced EMF is zero. There is no induced EMF. So induced EMF, one must be in motion between the coil and the magnet. There must be relative motion between them. Now, you can see now as well in number D there, in alphabet D, you will see that they are saying when the magnet goes away, the coil becomes north. No. Remember, it becomes north when the magnet goes inside, is pushed into the coil. So you can see that this is wrong because when it goes away, we expect this to be south so that we can have a change in magnetic flux. It's saying come back. When it's going away, it says come back. When it's going towards, it becomes north. It says no, I don't want you to come. So that's what happens. So you can see the north is approaching. We expect this to be north so that it can repel. So number B is wrong because it must be when north approaches, the coil will be north. When C is wrong, because when the south, you can see the south pole now is moving away, you expect that this must be north so that it can pull it back and bring it back. The same with D. When it north moves away, this must be south. So you can see that the only option that is correct is our answer there that we have given as A there. Now we move to baseline activity number 2. I hope that activity it helped you to understand that when the north approaches, the coil becomes north, so that it can have a change in magnetic flux. When the magnet goes away, when the south is going away, the magnet becomes north, so that it can attract it. So you have that understanding. Now let's move. This one is saying a circular coil is placed inside a magnetic field. So now if we bring a coil, we put it inside the magnetic field and rotate it clockwise. You see, we said there must be movement. It's now being rotated clockwise to induce an EMF. Which one of the following changes will increase the induced EMF? We're going to do this even in this lesson to say, how do we increase the induced EMF? The EMF that is being induced, how can we increase it? So in this case, they are saying number A, if we rotate the coil slower, you will see that if we rotate the coil slower, definitely the induced EMF will decrease. If we rotate, it means we must increase the rotation of the speed of rotation of the coil. That's what will increase the EMF. So this cannot be correct. Number B is saying when we decrease the number of turns. Decrease the number of turns. No, we want to increase the windings. We must increase the windings, meaning that this will decrease the induced EMF. But look at number C there. It's saying increasing the speed of rotation. Definitely, when we increase the speed of rotation of the coil, remember one of them must be moving, and then we are saying when we're moving faster, you are increasing now the induced EMF. So definitely, number C will be our correct answer. And we're saying changing the polarity of the magnets is not what is going to increase the induced EMF. What will increase the induced EMF is to increase the speed of rotation, or to increase the number of turns or windings, and rotating much faster. That's what we are referring to. So I hope these examples already, they are making you to remember what you have done. Now the last thing on these baselines that we are doing is to say the north pole of a bar magnet is pushed into a solenoid. Remember, we will be referring to a solenoid, to a coil, to an armature. In your mind, you can see that we are referring to all that. To say this is our solenoid. So don't be confused with the language there. When we refer to the coil, when we refer to the armature, when we refer to the solenoid, have that understanding of saying this is what we are talking about. We're having the magnet, we're having the solenoid, the armature, the coil, and the principle is the same. In which direction will the induced current flow? Right only A to B, or from B to A. Very much important. Remember, the inducing action, the magnet is moving in that direction. So if the inducing action is the movement to the right, definitely the induced current must be in the opposite direction, which is from B to A. So that's how you'll have to have that understanding to say, okay, if we are inducing by moving the magnet in that, the magnetic field is moving in that direction, the induced current will be in the opposite direction. We'll talk about that as well when we deal with this topic. I hope the baseline now has opened your eyes to say this is what we're going to focus on. And you can see we're dealing mostly here with the generator, where we're moving the magnet into and out of the coil. And we're saying as we move the magnet in and out of the coil, there will be change in magnetic flux. And immediately when we stop moving the magnet, we are saying as long as the magnet or the coil, both of them are not moving, there will be no change in magnetic flux. And when there's no change in magnetic flux, there will be no induced EMF. So EMF will be induced when there is interaction between the magnetic field and our coil there. So I hope we are together in terms of that. Now, let's do this one, which was based on calculation. You are given a circular coil of radius 3 centimeter, which contains 150 loops, and there's a resistance of 10 ohms. This you have done as well is your grade 11 stuff. And we're saying it is positioned perpendicular to a magnetic field of strength 3,8 T. The coil is pulled from the field in 0,2 seconds to a point where there is no magnetic field. Now we're saying calculate the change in magnetic flux in the coil. Calculate the change in magnetic flux in the coil. And then the other question was saying calculate the induced EMF. I've shown you the formula for induced EMF. And we are saying lastly calculate the induced current. You can see that the order there, that it is the EMF that is being induced. Remember, it's the electromotive force. So if we are having the force and we are having a closed circuit, definitely there will be flow of current. But current flows when we have the closed. You know that you have done electricity. You wrote about it in June exams. So you know that when we have a closed circuit, when you close the switch, you know that the circuit becomes closed, and when it's closed, current can be able to flow. So we're saying the same principle applies here to say, okay, if now we're having induced EMF by the movement of a coil or the movement of a magnet into or out of the coil, we're saying when that happens, there will be induced EMF. And when the induced EMF is there and we're having a closed circuit, definitely we'll have induced current. And I've shown you that the current will oppose the inducing action. You have seen when the north magnet was moving into the coil, what happened? You saw that the induced current was in the opposite direction. So those are questions that I expect that you are ready for them and you are able to answer them. And then we said you must be able to do the calculation. The change in magnetic flux in the coil. So that was the first question. So we are saying magnetic flux is given by that. Remember I said change in magnetic flux is that one. Then you're able to see that, which is now your B times A. And then very much important, your B, we're saying is your magnetic field strength. Magnetic field strength, which was 3,8 T. We don't expect you to, when you're doing calculations, to substitute the SI units. Just use the units at the end of the calculation. And we're still emphasizing that here we always write the formula, we always substitute, we write the answer, and then we write the correct SI unit, and then with the correct direction. Always. But remember, direction applies when you're dealing with the vector components. So in this case, you must be able to write the formula, but for you to substitute, you must do data collection to say, okay, B is magnetic field strength is 3,8 T. And then you go back and you say the coil is put from the field in 0,2, 0,2 seconds to a point where there is no magnetic flux. But now, don't forget, we're given the radius of 3 centimeters. So you are able to see that, okay, now we can be able to calculate the area, which is pi r squared there. Pi r squared, and then you get your area, and then you multiply the pi r squared with the 3,8, and it gives you now the magnetic flux in the field. And then what is the magnetic flux outside of the field? Remember, we're talking in the field. Outside the field, the magnetic flux was 0, and then you can be able to say change. Remember, for you to use EMF, the question said calculate change in magnetic flux. So you must be able to have the 2, so that you are saying you subtract the 2. In this case, you have the 0, which is the outside, and then inside you have the negative 0,011, and then you get that negative 0,11. Remember, when we were writing the formula, we had a negative n there. That negative n, you can see that with this negative, they will cancel one another. It's important that you get an answer of that magnitude. Now, the second question was calculate the induced EMF in the coil. And then for you to calculate the induced EMF, definitely you're going to fall back to your formula there to say, okay, what is happening here? The EMF is that we are looking for, and then we're given the number of loops there, 150, which is your n there, and we were able as well to calculate the change in magnetic flux, which was negative 0,11. So you can be able to see the relationship and how this now connect to where we're going. So we're able to calculate the induced EMF, which is in this case is 8.25 volts. I hope you get that, and it helps you as you go on with the rest of your calculations. And lastly, it is the current. Remember, it was the EMF. After the EMF, it is the current. Remember, you know the formula V equals to IR. So the V here, we're talking about V total, which is your EMF. Your V total, your EMF there. You are saying EMF, and then you are able to do the substitutions. Remember, we are always encouraging you to say, don't just write the formula and then substitute, then write your answer. Then you simply substitute there, and then you get your EMF was 8.25. You get your R was 10 ohms, and you just divide by 10 both sides, and you are able to get a current which is 0.825 amperes, and then you are able to move. So that is what you have done in grade 11, and we are saying we are building from that information. Hence now we are moving to grade 12 to add now to say on top of that knowledge that you are having, this is what we are bringing now as brand new information that now you are able to connect and build a bigger house and understand the entire topic. Now, we're going to talk about motors and generators as I indicated. And they have the same basic components and operate on the same basic principle. And the components that you should have seen that when we're dealing with our magnet, when the magnet was moving in and out of the coil, you have seen that the components that we focused on was the magnets and the coil. The magnets and the coil. And I said sometimes we'll talk about the coil, we'll talk about the solenoid, we'll talk about the armature. Have that in mind, that if we say the armature or the solenoid was still, the signs is still the same, it's not changing our signs. Now, slip or split ring. Now, this is new information to you. So now we have slip and split ring. You see, it's not slip of sleeping at night, this one. It's slip, S-L-I-P. So we call them the slip rings. So we're going to look at the slip rings. You will see we use these slip rings in AC, motors, or generator. So to know whether a motor or a generator it is AC, it must have what we call slip rings. So we're going to look at the structure, how to draw, how is it drawn, how does it look like, these slip rings, so that you are able to look at that. And then the split ring is what we use now in our DC motor or generator. So we're saying in both a motor and generator, we have AC and DC. How do I know it's AC? I will look for the slip ring. How do we know that it's a DC? I will look for the split rings. These split rings have another name. We can refer to them as commutators. So it's important that you know that we can call it commutators, or we can call it a commutator or a split ring. So it's important. So we're saying AC is slip ring. DC is split ring. That is for DC, motor, or generator. So both motors and generators, we have DC motor and DC generator. We have AC motor and AC generator. So it applies to both generators and motors. So we're saying generators and motors, when they have slip rings, we call them AC. When they have split rings, we call them DC. And then we are saying the split rings has another name called commutator. So we use them interchangeably. So it's important that you know that the split rings are the commutators, so that you are not confused. Now, the principle, the issue of principle, remember we said there must be changing magnetic field. And you have seen what changes magnetic field, because you have seen that when the magnet moves in and out of that coil, there will be change in magnetic field. And that will induce an electric field. So you are having the magnetic field that induces the electric field. And then the magnetic fields will interact with one another. And then the basic difference, what are the differences between these motors and generators? The basic difference I already told you at the beginning of this lesson, to say the basic difference between electrical motors and electrical generators is that hence they are called generators, they are generating, is energy conversion. So for a motor, it converts electrical to mechanical energy. And then for For a electrical generator, it will convert mechanical energy into electrical energy. Example, we have a bicycle lamp there, and then as you are driving your bicycle there, you see that the bicycle lamp is lighting there because there will be what? Mechanical energy. That rotation, mechanical energy is being converted to electrical energy. And then the motors here, we can talk about the electric fan. I think you are aware of the electric fan. You are always connecting it to a power source. It always needs a source. And hence we're saying motors. How will you know that this is a motor? It will have a power source because it's converting electrical energy to mechanical energy. I hope you are moving and enjoying the lesson as I'm doing. Now, what are the main differences between this? Already I told you that the motor uses electricity because it converts electrical energy to mechanical energy. But when it comes now to the differences, we are saying a generator will produce, it converts mechanical energy to electrical energy. 100% we are able to move. You see the difference between a motor and a generator. So this is a nice section that we're expecting you to collect these marks for this section and do very well. And if you follow this lesson, I'm telling you, you will definitely enjoy and be able to collect many marks as you are expected to. Now, I told you already that both motors and generators, they have the direct current motor, direct current generator. So a direct current motor and a direct current generator, let's look at them. What makes them direct current? You can see this guy I was telling you about. This one, you see this one in yellow, that one. That is what we call now a split ring. Remember I said a split ring has another name. Another name of a split ring is commutator. So they have a commutator, this one, commutator. Okay, they have a commutator. Why do we say it's a split ring? You can see it's like a ring, one ring that has been split into two. And when you look, you can see the D's there. The D is there. You can see the D's. So you know that when I have something like that, when it's like a D looking that side and another D looking, that is a DC. Is it a motor or a generator? Say, how will I know that this is a motor? It has a power source there. You see, we're having a cell there. We'll have a cell or a battery. And then when we have a cell and a battery, we know that now we have a source. We're talking about a motor. And how do I know that this is a generator? There must be output. You can see we have a voltmeter there that is measuring the current that is being or the EMF that is being induced in that particular generator. Remember the generator, we said it converts mechanical energy to electrical energy. So you are able to see that, okay, on this one we have a power source, hence this is now a motor. A motor we need, hence we talked about electrical fan. The fan you are using it to, we said you need to plug it on the wall there. Then you are having now be able to utilize it so that the motor now needs power source. But the generator does not need power source because it's producing the electricity. We are converting mechanical energy, which means what is important is that there must be rotation of this armature. You see now we are referring to the armature. So hence I said have the language with you so that you don't get confused. I was talking about the coil, I was talking about the solenoid, now I'm talking about the armature. So you're able to see our armature there, and then you see that is in between the magnets. So two things that you need there. You are having current and magnets. You know magnets have magnetic field. Magnets have magnetic field. And remember that your grade 10 syllabus, grade 11, you have learned that the magnetic field, they flow from north to south. So you know that you have magnetic field that are flowing in that direction. And your current now, sorry for that. The current that we're having is that the current is conventional current. Our current flow from positive to negative. So you can see there we have shown you the direction of the current. It's okay, the current will be in that direction, the magnetic field will be in that direction. So you are able to see that, okay, this is what is happening in terms of this one. Now, the other piece of information is that on the generator side, here we had a source, we had a battery, and we were saying our current is flowing from positive to negative. It's flowing like that from positive to negative. And then we were able to say now current is conventional, positive to negative. The magnetic field is from the north to the south. So you're able to see all that. And definitely, because there's going to be interaction between the current and the magnetic field. Remember the coil there. The coil there now is horizontal. So we are expecting that there will be maximum interaction between magnetic field and the current that is moving there. So you are able to see that here we're expecting that now there's going to be a maximum utilization or maximum force that will be heavy because of the how the coil is. So that is important as well. Now the other thing, remember when it comes to the generator, we are starting now, we have the magnets that have magnetic field, and immediately we have now to rotate mechanical energy. It means we must now rotate the coil between those magnets. So as we are rotating the coil, there will be interaction between the magnetic field and the coil, and then we're going to have what is called electromagnetic induction, and we're going to explain it in full. And we are saying you are able to draw even the graph as well for direct current. The direct current, you are able to say for DC, and the graph we are expecting that. We always refer to it as a jumping frog, so that you remember. For DC, the graph will be like that. But if we're talking about alternating, you will see that your graph is sinusoidal. It's like your sine, you are doing maths, your sine graph. You are able to see that you will have a graph that is moving like that, because it shows that that is alternating. But in terms of this graph, we are saying it's a jumping frog, because its direct current is in one, there is no changing in direction. So it's a jumping frog as we indicated there. So you are able to see that the graph for DC, you're expecting a graph of that nature. The graph for a alternating current will be like that. But for now, our focus was on DC, and that is the graph that we are having. So I hope you are appreciating and seeing that this concept is very nice and straightforward. And even when we ask the questions, we'll ask the questions about the components, about how it is the electromagnetic, how the current is induced, and all that. And you are able to see that is your DC. Now, I want to further explain the movement or the generation or the induction of current. What happens, as I indicated already. So you will remember we said that if a magnet is moved relative to a coil, an EMF is induced. So you can see the south is being moved in. And the signs that we talked about, we said now your coil will do what? Your coil will be south. When the south approaches, the coil becomes south so that it can repel. And by doing that, there will be change in magnetic flux, because we are bringing the coil inside. And we're bringing the magnet into the coil, but the magnet itself is saying don't come in, but we are pushing it in. Hence, we have changed in magnetic flux. And we are saying as we move the magnet away, definitely when the south is moving that side, the magnet will say now I'm north. I'm saying come back. So that now there is change in magnetic flux. I think you appreciate that. And we are saying when there is induced EMF, if we have a closed circuit, remember for current to flow, it must be a closed circuit. There will be current in the circuit. So we have induced current. You see how current now start to flow, because we have the force, the EMF, electromotive force, but it now needs, this energy must be used. But for it to move the charges, remember the current we are saying is the rate of flow of charges. For the charges to flow, we need to have a closed circuit. Then we'll say current is induced now, because we're having a closed circuit. Now, when the direction of the movement changes, the direction of the induced EMF changes. Very, very important as well. So you can see when the magnet was moving into the coil, look at the current. The current is in the opposite direction. When the magnet is moving out of the coil, look at the current in opposite direction. So it's always important to know how will this induced current behave. It will behave like that, to say that when the magnet is moving into, you see that it goes the opposite direction. When the magnet is going out, it as well goes in the opposite direction. So it's always opposing. Yes, according to Lenz's law, that is not prescribed for us, but it's important that you understand that as the magnet moves in, the galvanometer there is showing you the current now, that the current will now move in the opposite direction. As the magnet moves out, the current will move in that other direction. So very much important. I hope you appreciate this slide and is able to help you. Further explanation is important, that because whatever that we're talking about is all about the induced the change in magnetic flux. So remember, no change in magnetic flux, no induced EMF. So we must appreciate the importance of this change in magnetic flux. Hence, I'm still indicating the direction of the induced current is such that the magnetic field it established tends to oppose the cause of induction. So it always opposes the cause of induction. If a north pole approaches the coil, for example, the north pole approaches the coil, you can see we're having a north pole that is approaching the coil. What happens? A north pole is induced. Here it becomes the north pole in the coil to repel or to oppose the approaching magnet. And that is how magnetic flux is being changed. And then if the north pole now is withdrawn, the top end of the coil becomes the south pole, saying north, don't go away, come back. So when the north is leaving, the south, it becomes south so that it can attract the leaving magnet. And we are saying we use the right hand rule. It's used to determine the direction of the current in the ring. And then you are able to deal with that one. Now, Fleming left hand rule and right hand rule. So we have left hand rule for the electric motor, we're having the right hand rule for the electric generator. So always know that for motors we're using the left hand rule, and then for the generator we use the right hand rule. And you are able now to see and have appreciation of saying, okay, when we are having a current moving in that direction, you can see we're having now the magnetic field moving always from north to south. We're having the direction of the current, and then we're having the direction of the force. So the force will be in that direction. So always know that we use the left hand rule for the electric motor, and we use the right hand rule for the generator. And then you are able to appreciate that. And we are saying for the right hand rule, we are saying when the current is moving that direction, the magnetic field is moving from north to south. So you are able to see that, and then you are able to see that we'll have the force now, the motion now in that particular direction. So as we have applied it there, the right hand rule. So it's important that you are able to differentiate between the left hand rule and the right hand rule. And we are saying the right hand rule states that the magnetic field lines produced by a straight current carrying wire will be oriented in the same direction as the curled fingers. The curled fingers, they are showing you now that are magnetic field lines. As the curled fingers of a person's right hand, so holding like that, these curled fingers will be the magnetic field. And then with the thumb pointing to the direction of current flow, the thumb showing the direction of the current flow, or the variation of it. And then you can see we are having a variation like that. If you make the fingers of your right hand follow the direction of the current in a loop, your thumb will point in the direction of the North Pole. So your thumb like that is showing you the North Pole where it is now. Magnetic flux, talked a lot about it. Important. When you know magnetic flux, you know this section. You know how it's generated. We talked about it. How we generate it. It represents, we're saying it represents an imaginary fluid. So you look at these lines as being like a fluid that is flowing. It's flowing from the north to the south. That is our magnetic flux. And then we're saying the strength of the magnetic field depends on the density of the flux. Is how many of these lines are closer to each other. When the field is strong, the field lines are closer together. When these field lines are many and closer together, we are saying we have a strong magnetic flux. And then we did this, the magnetic flux, and then we said is the magnetic field multiplied by the area perpendicular to the flux lines. And then we did even the calculation, and then I hope we have all that. We talked about Faraday's law. We said it's the rate of change, or you are saying the induced EMF. The induced EMF is directly proportional to the rate of change in magnetic flux. So you are able to do that in that is that. When you put the directly proportional, you can remove the minus and the number of loops, then you get it directly proportional there. So you can see that the induced EMF and time, they are inversely proportional. But the induced EMF and change in magnetic flux, they are definitely. So it means if we are slower, we're taking more time, we are slower, we're increasing time, the induced EMF will be less. But what happens now when we decrease time, when we change the magnetic flux by moving the magnet in and out of the coil much faster, we're increasing the speed of rotation, you see the induced EMF will definitely increase. And that is the science behind it. And then let's look at the comparison between your motor and your generator. How do I compare them? A motor, we are saying this one, I won't forget, is always from electrical energy to mechanical energy. Always when we're writing in our exams, write in full. Write in full, because when we're in the exam room, we want to see electrical energy to mechanical energy. Energy is converted from electrical energy to mechanical energy. And when it comes to the generator, energy is converted from mechanical energy to electrical energy. So you are able to see that. Now, a motor, we said split rings, they have to do with DC. They have to do with DC, and then they will use the split rings for reverse current, split rings for DC output. So you know, split rings, DC. AC supplies replaces commutator, and then we're saying slip rings, AC output. And then we're saying the current in the magnetic field, then it forces the force is being generated. And here the motion in the magnetic field. Remember we said when you rotate the armature between the magnets, in the magnetic field. So there must be motion in the magnetic field, then there will be induced EMF. And if we have induced EMF, we'll have current that is flowing if we have a closed circuit. And we're saying we can increase this force by using stronger magnets. Don't make a mistake. A bigger magnet is not a stronger magnet. Stronger magnets is the strength in the magnet. We're not talking about the size of the magnet, but we are talking about the strength that magnet has. And we're saying having more turns in the coil, and then stronger current through the coil. And then in terms of the generator, we can use stronger magnets, and then we can have more turns in the armature coil, faster rotation. More turns, faster rotations, all will do that. And you'll find this question that asks you, how can you increase the induced current or the induced EMF? And then you are able to know that I must use stronger magnets, I must have more turns in the armature coil, and I must have faster rotation of the armature. So I hope we are moving together and you are starting now to appreciate this section, and that this is where you must work and do many questions and be able to get this correct. And we are saying there are two things that are important to note here. We are saying there must be change in magnetic flux. There must be change in flux linkage or magnetic flux to the coil for current to be induced. So you know, how do we change the magnetic flux? We said there must be continuous, that movement of the magnet or the coil, because I don't want you to cram and think that it is always the magnet that is moving. It can be the coil that is moving. When we are even around the magnet, it's still fine. Now, number two, we are saying there must be changing a magnetic flux to the coil for current to be induced. Number two, we are saying the maximum EMF is induced when the area of the coil is perpendicular to the flux line. The area of the coil is perpendicular to the flux line, then we'll have maximum EMF. That brings us to a different wording of electromagnetic induction. This electromagnetic induction, we're saying, is the process of generating electricity, because we said here we're talking about now, it is a principle that is used by generators, and the generator, they convert mechanical energy to electrical energy. And how do we do that? By changing the magnetic field acting on a conductor. How do we do that? We are moving the magnet in and out of the coil, and we indicated what can be done to increase the induced EMF or the induced current. So we can be able to move. Now, we said when the movement of the magnet is continued, the current is continuously induced. So you got to have that appreciation to say there must be continuous movement of the magnet or the coil. There must be continuous movement. Immediately when you stop, no movement of the magnet or the coil, no induced EMF. And we're saying the induced current is alternating current. Remember, we're talking about the alternating current. Say the movement of electric charge periodically reverses direction. I've shown you when I was saying when you draw the graph for induced EMF, you will draw it like that. When you draw the graph for the DC, I said you will draw the graph, that jumping frog, like that. Oh, my drawing. I wish I can be a good person in terms of that. It's a skill that I must improve on so that I can be a good person. I think I've drawn much better. That is, will be direct current in one direction. The flow of electric charge is only in one direction. But for alternating current, movement of electrical charge periodically changes. So you can see it reverses direction like that. So you are able to see the AC graph and the DC graph. And we are saying alternating current is only induced while the magnetic field moves relative to the solenoid. When there is a change in magnetic flux linkage with the solenoid, we talked about its direction keeps changing, hence it's called alternating current, AC, because the direction is always alternating, meaning that if you are drawing the graph of current, it will be like our current will be alternating like that. Our voltage, so it can be the graph of voltage or the graph of current, it will be alternating like that. And we have talked about this to say how do we increase the strength of the induced current. We are saying that we increase the strength of induced current by increasing the speed of the movement of the magnet. So that magnet, if we're moving it in and out faster, we are saying that we're increasing the induced current, induced EMF, by implication induced current. If we use a stronger magnet, I emphasize that not bigger magnet, but stronger magnet. And we're saying when the number of turns in the coil increases, when increase the number of turns in the coil, as well, that will happen. And remember at the beginning of this lesson, I indicated one of the objectives was to find the advantages. Why do we use, not especially in our case, South Africa, why do you use AC over DC? Why the electricity that we are using, that is we are using at our homes, is being transmitted as AC, not DC. So the advantage is that the voltage can be changed. So we're saying this voltage can be able to be stepped up and stepped down. So we're saying we can be able to transmit large amounts of voltage, but now we have your power stations that can be able to reduce that load, so that the one that is transmitted to our homes is what we need, which is usually 220, 230, 240 volts around there. So you are able to know that they can bring thousands of voltage from where they are generating the electricity from, and then they transmit it AC in large amounts, and then that large amount can be able to be stepped down, can be able to be decreased to the level that we are able to utilize at our homes. Hence, it's important that we use AC. So that is one of the main advantages, that it can be changed. It can be stepped up or stepped down, because this property, the current induced by a power station, is alternating current. So from the power station, we're using alternating current. I've been talking. I think it's important that you take an activity and check that you were listening as we were talking. I won't give you much time. I'll just give you just 5 minutes to answer that question, and then I will see you after 5 minutes when we do the corrections. And then I hope you are moving with me and you are having the appreciation and understanding of the topic. Thank you. See you in 5 minutes. Welcome back. Welcome back. I hope you have done the activity and you have enjoyed it. The first thing that we must appreciate is that we are having the magnet. The north pole of the magnet is approaching our coil, and what the expectation is that now there will be change. As long as there is movement of the magnet into the coil, there will be change in magnetic field. There will be change in magnetic flux, and then we as we are saying now, as the north pole approaches, we are saying that the coil now will now be north pole, so that it can repel or oppose the incoming north pole. So it will be north pole, that is the reaction, that the north pole will be used there so that it can repel that one. And then in terms of current, remember we indicated the importance of that to say the current now must oppose. So you can see our current there is going to oppose, is moving in that direction, which opposes the movement. As you can see, it's moving like that to oppose the incoming one. So always you are checking at how the magnet is moving and the current. Which means when we pull the magnet outside, you will see that the galvanometer will oppose, meaning that the current now will flow in that direction. So it's important for you to explain and to write it in correct way. You will say the magnetic flux link changes. So there will be change in magnetic flux. That is the first mark. The second mark was saying the coil induces a north pole on the left hand side to oppose the incoming north pole. I hope you are marking yourself there to say, okay, what happens in terms of the current? A current is induced when the coil is connected to a closed circuit. So as long as we have induced EMF and a closed circuit, we'll have an induced current. And what is the direction? We're saying the direction of the current can be determined by the variation of the right hand rule, and then you were able to see now that the direction of the current is that one that opposes the inducing action. Now let's look at activity 2. It's saying, is the inducing of a current by changing magnetic field. By changing magnetic field, principle of electrical motors or electrical generator. You got to always remember that as long as we are inducing, we are generating, that is a generator. So definitely there is the inducing of a current by changing magnetic field will be electrical generator, not a motor. A motor does not induce, it converts electrical to mechanical energy, whereas a generator will definitely convert a mechanical energy into electrical energy. So that is your explanation. Name 2 conditions for the inducing of a current. Remember we said inducing current, there must be change in magnetic flux. When there is change in magnetic flux, we said the circuit must be closed, then definitely current is going to flow. And we said know the 3 ways in which the induced EMF or current in a closed circuit can be increased. Remember we talked about your increasing of the rotation, the use of a stronger magnets, and the faster rotation of the coil between the magnets and all that. So you are able to refer to all those and get all your answers. So we are saying here it is electrical generator, since it transforms mechanical energy to electrical energy. But the difference is, just look at the definition to say what are the energy conventions, and then you are able to see the difference between a motor and a generator. And then we are saying for current to be induced, we are saying there must be a change in the flux linkage or magnetic flux in the coil, and the coil must be connected to a closed circuit. And then to increase our induced EMF or induced current, we are saying that there must be increase in the speed of movement of the magnets. We must use stronger magnets. We must increase the number of turns in the coil. Please always remember that if you get that question in the exam, you are able to respond to that type of a question. Now, activity 3 there. We are saying now, which of the following statement describes an alternating current. So now you see, now we are moving. Now we are doing the multiple choice questions, and we are saying multiple choice questions are questions that every learner must respond to in the exam. Please don't leave blank spaces when you're given multiple choices. Remember, you have 4 options to choose from. Please, I'm pleading with you, write something. There must be A, B, C, or T. You can't say 1.3.1, 1.1, you leave it unanswered. 1.2, you don't answer it. Those are multiple choice. You have 25% chances of getting the correct answer. So don't leave multiple choice questions unanswered. And we're saying you are always given 4 options in our physical sciences multiple choice questions. And we're saying of the 4, 2 we refer to them as distractors, which are obviously wrong answers. So always identify the distractors and remove them so that you remain with 2 that are closer to the answer. Then you are able to look between them closely to say which one is the correct answer. So I'm saying, as a strategy, always remove the distractors, and after removing the distractors, ensure that of the 2 options that you are left with, you choose the correct one and be able to get all the multiple choice questions. And then let's look at this one. It's saying, which one of the following statement describes an alternating current? So we're looking at alternating current. We're saying it is produced by a battery. We are saying electrons change direction continuously. Or alternating, changing. To alternate is to change. So, there must be change in direction of what? Of our electrons. Remember when I started, I said this term is the term of the electrons. Remember, you'll be doing photoelectric effect, which is about the electron. You'll be doing galvanic cell, which is about the loss of electron and the gaining of electrons. You'll be doing electrolytic cells, which is about the electron. So this term is the term of the electron. And once you appreciate the electrons, I'm telling you, you will enjoy this subject. Now, we're saying it is produced by a power plant. I think we talked about this one to say in South Africa, our power plant are producing AC because they can be changed. The voltage can be changed, can be stepped up and stepped down. And then we're saying in that way, it becomes easy for transmission. I think you can see Roman figure 2 and Roman figure 3 are talking to us. But now, Roman figure 4 is saying electrons move in the same direction. Same direction is direct current. So this one is obviously a distractor. Cannot be an option. And here we're saying a battery, or the batteries that we are using. No, we talked about the power plants and all that. We are saying the battery, it must be DC, that one. Then we are saying no, it cannot be AC. Then we are left with Roman figure 2 to say the electrons change direction continuously, or the current changes direction continuously. It is produced by a power plant. We are agreeing with those, and you can see definitely that B is our answer, and you are able to get your 2 marks with no problem there. And then we are saying now, in a coal-fired plant, steam is used to turn the turbine blades. Now they are using steam to turn the turbine blades, and then we are saying the type of energy conversion which applies here. Remember, in a power plant, we're generating electricity. Definitely, it must be mechanical energy to electrical energy, which in this case, we gave you as number A. Definitely, you are getting your 2 marks for saying A is the answer there. The last question, which is 3.3, is saying an electric current flows into a page. It flows into the page. What is the direction of the magnetic field? What is the direction of the magnetic field when the current is into the page? And then what is the magnetic field? So you are able to see that the magnetic field, definitely it must be in a clockwise. So you are able to see your answer there as alphabet number C. It will be C there. So you are able to see that those are your answers for the questions that we're doing. And then let's look at this direct current. already I told you, direct current, what do I look for? I'm looking for the split ring. You can see it's a ring, but it has been split. And you can see the D there. Don't forget your D there for the DC. You see that this is our DC, and then it will be DC. Although the current in AB turned around the coil, not turned, but we are saying this branch receives the current all the time. So you can see that this is what is happening in terms of the split ring. Remember we said we call it split ring or commutator. So you can refer to it as a split ring or commutator. And we talk here to the issue of fluctuating current, which is your alternating current. Now your current now will be fluctuating. What makes this current to fluctuate? So you can see we're saying when depending on this, let's look at this armature that we're given there. This armature that we're given there, we're saying now depending on its direction, when it's at 90 degrees, the long sides are at right angles to the magnetic field. EMF has a maximum value. So I want you to have a bigger understanding and appreciation. So we are talking now when it's like that, is maximum. We're having maximum EMF. But immediately when we start to move it, you can see now it's rotating in that direction. When it starts to rotate like this, so when it's the magnet north pole, south pole this side, and we're having our magnet like our coil like that, or our armature like that, the magnetic field this side, we're saying that is when we're having maximum EMF, maximum induced EMF. Immediately when the armature rotates, the angle now is changing. Immediately when we change the angle, the EMF is decreasing. And when it's at 0, the long sides are parallel to the direction of the magnetic field. So when our coil, take this as your coil, when our coil is in this direction and we have the north and the south here, we are saying now the magnetic field, remember there's nothing here in the coil, the magnetic field lines are not interacting with the coil itself. Hence we are saying that now the induced EMF would be 0. So you got to appreciate the direction to say it's always important that when it's like that, you are having now a maximum EMF induced, but immediately when our armature coil start to rotate, the EMF is decreasing, and then in that direction the induced EMF becomes 0. So you know that we have 0 EMF, induced EMF, in that particular direction. So it's important that you have that in your mind. And then for our DC, we are saying, yes, I like this and this one, this slide, look at it and have understanding, and you'll have appreciation of these graphs. To say when you are having our armature or our coil in this position, you can see that in this position at 0, we are saying now there is no interaction between the magnetic field and the coil. Hence we are saying the induced EMF will be 0 degrees. So 0 degrees, it means that there is no interaction between the magnetic field and the coil. Now when the coil now starts to decrease in terms of moving, now the angle now is decreasing. You can see now when it moves in that direction as indicated here, you can see that the induced EMF starts to increase. Immediately when it's horizontal like this here, that is the maximum. So it's important that you understand that 0 is when it's at that angle, which is now vertical. But when it's horizontal, that is the maximum that we are having on the graph. Please have that appreciation. I'm telling you, will enjoy. As the coil starts to rotate and move again, and then you can see the EMF is starting to decrease as the angle decreases. And then you can see that when it's vertical again at 180 there, it is vertical. The induced EMF is 0. Here at 90, it was maximum because it was horizontal. And then at 0, it was 0. Induced EMF was 0. So always when it's vertical, you see that there will be 0 EMF, induced EMF. But immediately when it's perpendicular, remember we talked about the magnetic field must be perpendicular to the area. So that is what we're talking about. So you got to always appreciate that when it's horizontal like that, we'll have maximum induced EMF. But when it's vertical position like that, you know that it will be a zero induced EMF. And as it moves like that, and this is the graph for direct current. And I've shown you that the graph for alternating current will be in that induced EMF will be in that direction because it periodically changes direction. The induced EMF periodically changes direction. But this one, we said it's a jumping frog, so it's in the same direction. So you see that this is the graph of DC, and then you are able to see what is happening. I hope you have appreciated that. To say zero is when it's vertical, and as it becomes horizontal, the EMF starts to increase. When it's horizontal, we are saying now we'll have maximum EMF, and then you have induced EMF at maximum. But immediately when the changes now, the angle starts to change now, going back to vertical, the EMF decreases, and when it's vertical again at 180 degrees there, we have zero. So I hope you have now the appreciation and understanding of the meaning of those things. So you're able to see that when I see zero, I will see that okay, that is when the coil was, or the armature was vertical, and then you are able to have that. And then the strength, we talked about this one, the strength of induced current will increase by increasing the speed of the movement of the magnet by using stronger magnet and increasing the number of turns in the coil. We talked about that. Have that in your mind to say how to increase the strength of the induced EMF or induced current. And then a simple question for you to look at and do to say what type of a generator is this? The first question you must ask yourself, how do I know that this is a generator? I know that this is a generator because we said the motor needs a power source. This one, we just have the galvanometer that is just showing us the direction, and the statement as well told us that a simplified sketch of a generator. So always read, because as you are reading, either will tell you that it's a generator or will have an output. We can have a voltmeter. We can have, in this case, we have a galvanometer that will show the induced current, how is it moving, and that because we have shown you already that how the induced current move. Now, what type of the generator is this? We're saying is direct current. Why? Because you see there the split ring. Remember, the slip ring, they are looking like that. This is our slip rings. So in terms of slip rings, they are like that. You see something like that. They are just two like that. But split ring is one ring that has been split. You can see it's a ring. It has been split into two, and then those are split rings. And these rings, they have brushes. Both the split rings and the slip rings, they have brushes. We call them the carbon brushes. Carbon brushes, which are for electrical contact. So we have the carbon brushes here, which are for electrical contact, because remember, the charges must be able to flow in this particular generator that we're having. And you know that if it's a generator, there must be that movement of the coil with respect to the magnet, so that we are able to induce current. And we say generator uses electromagnetic induction to induce current. And then, so this one we're saying is a what? It's a generator, and we said to explain that you will always refer to energy conversion to say it converts mechanical energy to electrical energy. And give another word for split rings. We talked about that to say the other word for split rings is commutator. And then 4.3, we're saying show the value of the EMF on the graph that correspond with the position of the armature. You can see that the armature is horizontal, and we said it's DC. So definitely you are going to draw the graph like that and be able to say the value that we're talking about, the maximum EMF is there. That is our maximum EMF here, because that's what we are having. We are saying at this position, when it's horizontal, there is now maximum. So you can show it like that, or else you can just draw the graph. When you're starting the graph, when it's like that, it's starting the graph from maximum. So you can draw the graph from there, and then the graph goes like that. So you can draw the graph like that to show that we are starting from maximum. You know, if it starts to rotate, it will decrease to there and then increase like that. But it must be direct. It must be direct current, because now we're using the DC, that split ring, the commutator. It tells us that this is DC, and DC we're saying is in one direction. Our current is flowing in one direction, does not change, and then you are able to show that in the graph. What type of energy conversion takes place in a generator? We know energy conversion in a generator, we said, is from mechanical energy to electrical energy. What is the essential difference in the design between the DC and the AC generator? We talked to that one. To say DC, they will have split ring, which is just a ring that has been split, and then the AC will have slip rings. So we're able to see the difference between them and be able to move like that. And then you have there your nice homework that you will do and be able to answer that question. You can take a picture and be able to answer those questions and start to appreciate the topic itself, and then you do even more questions. And I'm telling you, as long as you have built today your confidence on electrodynamics and how to go about studying and having understanding, because we want you to have conceptual understanding of what is happening, and then you can be able to do many, and then you'll be able to solve as many problems as possible. So I just want now to summarize what we have done today, to say today we're able now to talk to DC and AC generator, as well as DC and AC motors. For DC generators, we said these ones, the DC, they have slip rings. You will see them, they have slip rings. But because they are generators, we said there must be output, power output. So they convert mechanical energy to electrical energy, both DC and AC. The difference here between DC and AC is that DC is in one direction, the induced current is in one direction. AC, it alternates, it periodically changes direction. So for DC is like that. For AC, we said it uses the slip rings and the carbon brushes. Remember, we're saying the carbon brushes are to bring the electrical component. And the principles, we talked about the principles to say generators, they use electromagnetic induction as the principle. Motors, they use the motor effect. We talked about the RMS voltage and RMS current for AC, and then we say the RMS voltage or potential difference for AC dissipates the same amount as the RMS voltage for DC. And then we talked about AC and DC graphs, and then you have seen we have talked about the jumping, but as well we talked about the meaning of that starting from zero. When starting from zero, you know that is when our coil is vertical. Maximum, that is when our coil is horizontal. And then that is for DC. For AC, we said it will alternate between the positive and the negative. It periodically changes direction. That's what we have done in this lesson, and I'm hoping we've laid a firm foundation that will lead to you having much proper conceptual understanding of this topic. And we are saying just in time, on the 1st of August, 2:30 to 4, we'll be doing photoelectric effect. Another topic, the whole topic, we do it. End of the topic, we are done with the entire topic. And we are saying thank you, and we close as we always do using Albert Einstein, who said, anyone who has never made a mistake has never tried anything new. So we're saying continue to try, continue to do as many problems as possible. And then if we do, this is our last push. We're expecting you that you have your timetable, you are revising every day, you are practicing as many previous question papers as possible. Till we meet again, thank you very much.